In our lectures on statics so far, you would notice that we have been taking the force on a body when it is on a surface mostly to be perpendicular to the surface. By doing so, we have been ignoring a very important force, and the one that is all the time present, known as the frictional force. And in this lecture, we pay attention to frictional force and discuss it in various different situations. So, to start with, frictional force could be between any two surfaces, and it opposes the tendency of motion. So, if a body tends to move in a particular direction, frictional force opposes it. Now, the frictional force could be between two dry surfaces, and this is known as Coulomb friction. It could also be between two surfaces that have a thin layer of liquid in between. This is sort of wet friction. Friction is also present when something moves in a liquid, known as the viscous force. In this lecture, we will be concerned primarily with Coulomb friction or friction between two dry surfaces. To understand friction, let us perform a small experiment. Let us take a block of mass m on a table or on a rough surface and push it by a force F. You notice that when force is small, the block does not move. It does not move because there is a frictional force opposing it. You keep increasing the force, the frictional force keeps on increasing, and it keeps the block in its position until you hit or you reach an F max. When you reach F max, the block starts moving. So, if I were to plot frictional force versus F, you would notice that friction adjusts itself with F up to a certain point, which I will call F max. This would be 45 degrees, so that the frictional force is exactly equal to the force applied. As you go beyond F max, the frictional force does not increase, it sort of saturates. So, what you would notice after this is that frictional force would tend to saturate at that possible maximum value. So, this is the maximum possible value of frictional force, and as you go beyond F max, the body would tend to move, because now I am applying a force which cannot be balanced. In practice, the line does not go like this, but when the body starts moving, the frictional force reduces a bit. So, actually frictional force looks something like this. When it starts moving, when you go beyond F max, frictional force goes below the maximum value of friction. So, we call these two regions, this is called kinetic friction and as long as the body is not moving, that is known as static friction. So, notice that frictional force, when you are applying a force on a body, is not constant. As you keep changing the force, the frictional force keeps changing until you reach a maximum force beyond which it cannot increase, and then the frictional force works at its maximum. What Coulomb observed is that this maximum value of the frictional force is equal to a constant which I will call mu s for static times n, the normal reaction on the body. This is the maximum possible value of static friction, and once the body starts moving, the kinetic friction F kinetic is equal to mu k, mu kinetic times n, and you can make out from this figure that mu kinetic is slightly lower than mu static. Although we write this formula F max equal to mu Sn, I again emphasize that this is the maximum possible value of friction. It is not that if I apply any force on a body, the friction value would be mu Sn. It will be less than mu Sn. As I keep increasing the force, the frictional force will also keep increasing until it reaches its maximum value, which is mu s times n. Mu s is known as the coefficient of static friction, and F max, maximum value of friction or maximum force up to which the body will not move, is mu s times the normal reaction on the body, and mu k, which is coefficient of kinetic friction. So, when the body is moving, the frictional force, I will call it F kinetic, is equal to mu k times n, and it is observed that mu k is less than mu s. For example, for steel moving on steel, the steel on steel, obviously I am talking about dry friction, mu s is about 0.6 and mu k is 0.4. One thing about friction is that it is independent of the area of contact. So, having understood what frictional force is, how it comes about, now let us solve one problem with it so that we get a better feeling about it. The problem I am going to solve is, if I have a block of say 50 kgs on a ramp with this angle being 30 degrees, and let us say I tie it with a pulley and have another mass here, small m. I want to know for what range of mass m would this block of 50 kg remain static on the ramp, given that mu s, that is the coefficient of static friction between the two bodies, is 0.4. Why should small m have a range to start with? It has a range because there is frictional force acting on 50 kg block. Suppose there was no friction. Let us say that if there was no friction, what would happen? If there was no friction, only one particular value of m would balance the capital mass M. How so? Let us understand that. If I make a free body diagram of the 50 kg mass, it would have tension T pulling it up, force 50 G pulling it down, and a normal reaction from the surface. If it is not to move, then all the forces, summation Fx, summation Fy, all the forces should satisfy these two equations. Let us for convenience take our x axis to be in this direction and y axis to be in this direction. Then summation Fx equal to 0 gives me T minus 50 G sine of 30 is equal to 0. Let me go over to the next page. What we are doing is having a mass of 50 kg on a ramp of 30 degrees. When I make the free body diagram of this big mass, it has the tension T, normal reaction N, and mg pulling it down. This angle is going to be 30 degrees. So, summation Fx equal to 0, if I take this to be the x axis and this to be the y axis, gives me T minus 50 g sine of 30 equal to 0, and summation Fy equal to 0 gives me n equals 50 g cosine of 30 degrees. This gives me that the tension T should be equal to 50 g sine of 30 degrees. If I look at the free body diagram of the small mass m, it has a tension T pulling it up and mg pulling it down. So, T equals mg, and that gives me m is equal to 50 sine 30 or 25 kgs. Just 25 kgs would balance this mass on the ramp. What happens when you introduce friction? Friction provides an additional force that opposes the motion, and therefore, I can have a range of small mass m that would balance the bigger mass. Let us see how. Let us say first that I reduce this mass below 25 kgs, then the bigger mass would have a tendency to move down this way. If this has a tendency to move down this way, there will be a frictional force opposing it. And this frictional force that opposes it makes it possible to have mass m much less than 25 kgs and still have this block in equilibrium. Let us see how. So, this mass of 50 g now, if I make a free body diagram, has a frictional force, let me call it small f, acting this way up the plane. There is 50 g pulling it down, there is a normal reaction N and a tension T pulling it up. Again, taking this to be the x direction and taking direction perpendicular to the plane to be y direction, summation Fx equal to 0 gives me T plus F minus 50 g sine of 30 degrees is equal to 0. That is one equation, and the other equation that I have is N is equal to 50 g cosine of 30 degrees, that comes from summation Fy equal to 0. If I look at the equilibrium of small mass m, this has only two forces T and mg pulling it down. So, T must be equal to mg for equilibrium. So, under frictional force, when this bigger mass has a tendency to move down, the equations for equilibrium are going to be this. Notice I have written this to be small f, the frictional force to be small f, not mu n, because mu s times n is the maximum possible value of friction. If 50 g sine 30 minus T is such that it is below the maximum possible value of friction, the block will remain in equilibrium and F would be equal to that value which is less than mu n. So, let us look at the equations once more. So, I have this bigger mass which has a frictional force acting this way, T acting this way, normal reaction acting this way, and 50 g pulling it down, and the equations that I wrote were T plus F minus 50 g sine of 30 equal to 0, N equals 50 g cosine of 30 degrees, and T equals mg. Putting it all together gives me F is equal to 50 g sine 30 degrees minus T, or 50 g sine 30 degrees minus mg. Now, the maximum possible value that F could have is mu s times n, which is equal to 0.450 times 50 g cosine of 30 degrees. That is the maximum possible value of the frictional force. So, we have equation F equals 50 g sine 30 degrees minus mg, and F max possible is equal to 0.4, which is mu s times 50 g cosine of 30 degrees, which is equal to 20 g cosine of 30 degrees. So, therefore, if I convert this equation to get m, I get m g equals 50 g sine of 30 degrees minus f. When f is maximum, m is the minimum possible value of small m, that gives me equilibrium. So, m minimum, that will give me equilibrium, would be equal to 50, I am dividing by g on both sides, sine 30 minus f max divided by g, which is nothing but 50 sine 30 minus f max is 20 cosine 30 degrees g divided by g. So, g cancels out. By putting in the numbers, you get this equal to 25 minus 10 root 3, which is 25 minus 17.32 or 7.68 kgs. So, you see, because of the friction, I could have a much smaller value of small m, 7.68 kgs, and still the whole system would be in equilibrium. This is when the bigger block has a tendency to move down. So, on this ramp, this is mass m, this is 50 kgs. If I have 7.68 kilograms, m equal to 7.68 kilograms, this block is in equilibrium, although it has a tendency to move down. What happens when I start increasing the mass on it? So, I go beyond 7.68, maybe I make it 8, 9 kgs, 10 kgs, 11 kgs, and so on. When I increase the mass, I would increase the tension. If I increase the tension, I would not require that large a frictional force to keep the big block in equilibrium. So, frictional force will go below its maximum possible value, which was 20 g cosine 30 degrees. So, F maximum we had calculated was 20 times g cosine of 30 degrees. If I increase this mass, it will start going down. In fact, when m equals 25 kgs, and we had calculated earlier that for m equals 25 kgs, I do not really need any friction to have equilibrium, F frictional force would be 0. What if I go beyond 25 kgs? If I go beyond 25 kgs, this mass would now start pulling the bigger mass up, and the direction of frictional force would change. So, the other limit of this whole scenario is going to be, have this pulley, that if I increase this mass m, it tends to pull 50 kilogram mass up, and therefore, if I go beyond 25 kgs, this mass has a tendency to move up, and therefore, the frictional force on this would be in the opposite direction. The question we ask now is, up to what value of m can I go so that the system remains in equilibrium? Again, if I make a free body diagram of the bigger mass, it has 50 g pulling it down, normal reaction n, T pulling it up, and frictional force is in the opposite direction. This is x, this is y, summation fx equal to 0 now gives me T equals f plus 50 g sine of 30 degrees. T is nothing but mg, as we have calculated earlier, is equal to f. F is nothing but mu times 50 g cosine of 30 degrees and plus I have 50 g sine of 30 degrees. And therefore, if I put in the numbers I am getting as mg is equal to mu s 50 g cosine of 30 degrees plus 50 g sine of 30 degrees. This is the maximum possible friction. So, this gives me maximum possible mass m, that will keep the whole thing still in equilibrium. So, m max is going to be mu s, which is 0.4 times 50 cosine 30, which is square root of 3 over 2 plus 25, which gives me 17.32 plus 25 or 42.32 kgs. So, for m less than 42.32 kgs and greater than 7.68 kgs, in this range the system would remain in equilibrium.